Module 3.3, Implementing MD in Practice. So far, we have learned about classical mechanics, we have learned about the force fields and their relation to density functional theory and so on. But now we will learn some of the other important concepts that are important before running molecular dynamics simulations. So as I said, yeah, we will discuss about the practical aspects of implementing MD calculations, understand the inputs and outputs. We'll understand the statistical ensemble, integrators, time step, boundary conditions, thermostat, and so on, and some of the computational softwares that are useful for MD simulations. So this is a typical schematic of molecular dynamics simulation. So as we mentioned in the last one module as well, we assign initial positions and velocities. Then we compute interatomic forces based on the force field that we are using. Based on these forces which are acting on each of the atoms, we can move or update the atomic positions and velocity. From there, we can compute the thermodynamic variable, store the configuration, and update the time or do the time evolution and repeat it for a certain number of time we want to simulate. So let's unpack that. So let's first talk about setting up the systems or inputs. So very similar to what we did again in density functional theory, we will prepare the initial structure with atomic position, lattice parameters. These atomic positions can be obtained from X-ray diffraction, NMR, or can be obtained from large databases such as COD, Jarvis, Materials Project, OQMD, and so on. And typically, we want to simulate, and this is the difference between this DFT, is typically you want to simulate thousands to billions or trillions of atoms in molecular dynamics. And especially if you have smaller systems, which I mean by that is less than 100 atoms, we want to use DFT instead of MD. So again, MD is used for large scale simulations mainly. So as we talked about in the previous module, it's hard to decide what kind of potential to choose. Luckily, there have been several efforts from NIST, such as NIST Interatomic Potential Repository, Jarvis FF, Web FF, and so on. And also, each of the software, such as GROMACS, LAMMPS, and so on, also have nice documentation on force fields and their limitations and their strengths. So I would recommend checking it out if you have time to understand the strengths and limitations of these force fields. Sometimes we can find this force field. So sometimes we can find too many of them. So suppose if you go to the Jarvis FF and click on aluminum, you will get probably 30 of the force fields. This is the case where we want to choose one of the best one, based on the properties we want to simulate, and based on the property that is closer to the functional theory experimental data. Now, that may not be the case. Sometimes we have to develop our own force field. So this will not be the case of this particular module, but there are cases where force field do not exist. And in that case, students spend their entire PhD to develop a force field. Now, an important concept in molecular dynamics simulation is statistical ensemble. So real-world experiments often operate under specific conditions, such as constant temperature, pressure, volume. And statistical ensemble, which is basically hypothetical copies, allow us to relate the multitude of possible microstates, such as we are dealing with very high number of particles when you are simulating, for example, a toothbrush. If you want to simulate a toothbrush, there are a lot of atoms. Or if you want to simulate a block of aluminum, there are a lot of atoms there. So we may not want to simulate all of that because some part of that is actually repeatable. So in that case, we can do what we can do is do a macroscopic thermodynamic quantities are represented by averaging over all the microstates. So we can say, hey, instead of simulating the entire block of the toothbrush, we'll simulate only a certain part of the toothbrush, and that will be kind of the ensembling in a way. Hope that makes sense. So now there are different ways of ensembling in statistical mechanics. We'll not go in the detail of statistical mechanics, but I do want to point out some of the important statistical ensembles, such as microcanonical ensemble, which has fixed number of particles. So in a simulation box, sometimes you might imagine atoms are being added or subtracted. So that will not be microcanonical ensemble. For a microcanonical ensemble, the number of particles of the system, such as atoms, are fixed, the volume is fixed, and the energy is conserved. For canonical ensembles, such as NVT, we might fix the number of particles, we might fix the volume, but we may change or allow the energy to change, but keep the temperature constant. So this again depends on the problem you're trying to solve. There are also something called grand canonical ensemble, and here we have fixed chemical potential instead of the number of particles, and volume and temperature. And also there are isothermal and isobaric ensembles, so NPT. Instead of keeping the energy and volume constant, we will try to keep pressure constant. So and the number of particle and temperature constant. So these are the most commonly used ensemble. There are many ensemble, but these are the most commonly used ensemble for molecular dynamic simulations. Now, we talked about integration in the mathematical and programming foundations. So here we'll be doing something similar, but instead of using ODE int or any other method, we'll be using more sophisticated techniques. So integrator are basically algorithms used to model the time evolution of a system given its initial state using equation of motion. So basically, you know the state of a system at time equals to 0. Now you want to know the state of the system at time equals to 10 or time equals to t. So you need to integrate the equation of motion based on Newton's law to have the time evolution of the system or mimic the reality using integrators. So some of the characteristics of good integrators are they should conserve energy and should be time reversible. So time reversible means if I go from 0 to t and come back, I should be able to come back from t to 0. So that is time reversible. And it should conserve energy, which we learned about as one of the fundamental laws in physics or chemistry. It should be efficient. So it should also allow longer time step. We'll talk about the time step. So basically, if you remember, when we were solving the finite difference equation in the mathematical foundation or programming foundation module, there we had to choose a interval h, right? So here in this case, we have the t basically. So those, the smaller, the better. But if you have very small time step, it might take a longer time to simulate for simulating a large time scale. So if you want to simulate 1 second or 1 picosecond, and if you have a time step of 10 to minus 15 versus 10 to minus 14, 10 to minus 14 will be faster, while 10 to minus 15 will be 10 times slower, and so on. So it's important that we can use actually some realistic time step when we choose an integrator. It should be easy to implement. And there are many type of integrators such as Euler, Leapfrog, Verlet, Velocity Verlet, and Runge-Kutta. And the most prominent one is actually the Velocity Verlet. So let's talk about the Verlet method. So you might have seen Taylor expansion during an undergrad course. So basically, a very simple way to understand Taylor expansion is y equals to mx plus c, a linear equation. So here you have y, which is the output, and x is the initial position, suppose, and m is the slope. So y equals to mx is very simple expansion of y with respect to x, for example. But in Taylor expansion, what we're trying to do is, suppose we know the position r at time t, and we want to predict the state at time plus delta t, small step. Then what we can do, take the rt, the position at t, and get the derivative of position with respect to time, first order derivative, second order derivative, and so on, and multiply by their time step exponent, and which have some and the factors such as half versus 1/6 and so on. So that will give you something called Taylor expansion series, and at some point we need to truncate it. So usually they are truncated after second order or third order because of the computation expenses. So you can calculate r at t plus delta t, and also you can get a t minus delta t, that is backward in time. And you can, if you add these expressions, then you might get the one given below. So this was Verlet method. Now, let's talk about velocity Verlet method. So regular Verlet method has no explicit dependency on velocity and only on acceleration, as you can see in the previous slide. And it would be nice to have velocity as well to have better accuracy. So this is solved by the velocity Verlet algorithm. So again, we had the Taylor expansion of position R and velocity V, and given by R and V. So R, we do the Taylor expansion of R as follows. So very similar to the last slide, but here we also do the velocity based Taylor expansion. So we have velocity and the derivative of velocity, second order derivative of velocity, and so on. And then we can Taylor expand the acceleration, then rearrange and multiply by the time step divided by 2. There's a lot of derivation about that. And then from there, we can calculate the velocity gradient and the second order velocity gradient. And you can see when we're doing this, we can accumulate errors. So that this is represented by you see the symbol O, the order. So this is the order of delta t cube versus delta t square and so on. So there's a nice mathematical foundation behind it to get the velocity Verlet. So again, moving on from that, we can substitute the expression for second order derivative of velocity in that equation, and we can get this simplified expression of velocity at time equals to t plus delta t as follows, which is v at t, the time at t, the time set divided by 2 multiplied by acceleration, and time set divided by 2 acceleration at t, and of course you have the order of delta t cube as an error. So as a recap, so first we evaluate new position based on velocity Verlet. So R at t we know, and R at t plus delta t we want to predict. So we know the R at t, and then we multiply, we add that with multiplication of velocity and delta t, and plus the acceleration at t and delta t squared, where delta t is the time step. Now we evaluate the force and acceleration at t equals to delta t, and we can evaluate new velocities following this similar equations. And we repeat this procedure to get an arbitrary time, and simulation of the time is possible in molecular dynamics simulations. Especially velocity Verlet is especially used for molecular dynamics simulations. Now we keep talking about this delta t. So it's important to understand what this delta t should be. So the molecular dynamic time step is limited by the highest frequency vibration in the systems, and typically is 1/10 of the period of that vibration. So when you have two bonds, suppose you have a hydrogen bond, that bond in a classical picture keep vibrating, and if it's very high, then if you want to resolve that phenomenon, you have to have very small time step, if it makes sense. So suppose especially in the hydrogen bond, typically the highest frequency is 3000 centimeter inverse with a period of 10 femtosecond. And this is why usually in molecular dynamics simulation, you'll choose a 1/10 of the period of that vibration, that is 1 femtosecond. So on the picture I show you, 10 to minus 15 is where we choose the bond vibration, which is 1 femtosecond. And sometimes if you're dealing with a coarse-grained model, you might be able to come up with a higher time step also if necessary. But also it's important to validate that with experimental observation or density functional theory data before choosing a time step. But usually 1 femtosecond is a good time step. Now, another important concept is periodic boundary conditions. So consider a large box of length L, and this box can be infinitely repeated. So on this left-hand slide plot, I show you a red block, and which is kind of repeated. So basically the idea is, if you can simulate that small box, which is also, we can call it unit cell, that is repeated n number of times. If you can simulate that, then the idea is we can simulate the entire infinite system. So in that way, we do not have to do infinite resummation, and we can only understand or analyze the smaller system. And for that, there are certain approximations to have minimum image convention. So such as we have to take a cutoff, so where we want to cut, where to simulate the periodic box and so on. And it comes with some error as well. So those could be minimized as well. There are certain mathematical theorems to prove that as well. And this is a great simplification for solving, for example, a large system. So if you are simulating a toothbrush, for example, or a block of aluminum again, you can take a small portion of it and simulate it instead of simulating the entire system. So this is extremely useful and powerful technique. Now, what is temperature in molecular dynamics simulations? So in the last module, when we were performing density functional theory calculations, those were based on 0 Kelvin modeling. But most of the engineering problems involve temperature. So in MD, there is particular very famous theorem called equipartition energy theorem, which can relate the temperature to the kinetic energy of the system. So kinetic energy Ke is given by 3 over 2. N is the number of particle, Kb is Boltzmann constant, and T is temperature. So if you can calculate the kinetic energy, which we can also calculate the temperature as given by the equation below. And to have the temperature at a particular condition, we can use something called thermostats. So thermostat could be of different types like Anderson, Langevin, Brandenson, Neuseehofer, and so on. And in this particular module and tutorial, we'll be using Langevin. So let's talk about that a little bit. So in Langevin dynamics, it's very similar to what we try to solve in module 1, the damped oscillator problem. Remember? So there was a gamma or friction coefficient that we are trying to change and see the effect on the equation. So here, very similarly, we have the standard force coming from the force field, but in order to maintain the temperature, we have a damping constant that can adjust the kinetic energy, and that friction force and the random force are related in a way to that guarantee the NVT statistics. And usually this gamma parameter, it depends on the system, but usually it's 2 to power 2 to 5 picoseconds inverse. So Langevin is susceptible to a synchronization artifact. So it's important to use random seed when initializing velocity. What I mean by that is these Langevin is dynamics is very stochastic. So always we recommend fixing the random number generator before running the molecular dynamics. So one of the advantage of the Langevin is it can actually allow longer time steps. So there are other thermostat as well, such as velocity rescaling or Berenson thermostat, in which the kinetic energy velocity revised to produce desired temperature. You basically rescale your kinetic energy to kind of fix your temperature to what you want. Neuseehofer, Langevin we talked about in Anderson, where in Anderson we have momenta re-randomized occasionally. And that one is true NVT and true stochastic. So Langevin is also true stochastic and true NVT, but Neuseehofer is not stochastic. We talked about the temperature. How about pressure? So there is something called Clausius-Virial equation, which can be used to obtain pressure from molecular dynamic system. So we have seen this PV equals to nRT. So it's based on that kind of idea. So pressure and volume multiplication is given by the n, the number of particles, the Boltzmann constant, and the time, plus 1/3 of all the positions Ri of the ith atom and forces acting on it, the F, and their multiplication sum. So the sigma, or you can see the sigma sign, that is the sum sign you might have seen in other engineering courses quite often. So this is how we can calculate the pressure acting on a system. So because we know the position of the system at T equals to T or T at any time, and we know the forces acting on each atom, we can calculate the pressure. And we know the volume also. So there are certain varostats, very analogous to a thermostat, that are used to control pressure. Now, depending on the system you want to simulate, you might want to choose a right software. So there are different types of molecular dynamic software, and LAMMPS versus GROMACS versus AMBER, CHARM, OpenMM, and so on. And LAMMPS is usually used for solid mechanics or solid state problems, while GROMACS and others are used for macromolecular polymer simulation, but they all have similar implementation. So others can be used, but they might have for being used for one versus other application. And also some of them might have implementation of particular force field. For example, if EAM is available in LAMMPS but not in GROMACS, then you might want to use EAM in LAMMPS only. However, if you want to use something like CHARM, which is actually there in LAMMPS but may not be available in other software, then you may not want to use that. So they again they're all solving the Newton's equation. They have different type of input and output file format, and this very nicely available on their corresponding websites. So these people actually put a lot of efforts to have people users use their tools, and to make that happen, they make several examples, several tutorials, several documentation of each command, and so on, that is useful for running molecular dynamics. So another important aspect of MD or DFT or any other atomistic simulation is how to visualize the input and output data. So there are different softwares such as Vesta or Vitho, Visual Molecular Dynamics, and you might download and play with it. But for the particular module, we'll be using the LAMP's inherent visualizing tool as well as Matplotlib. But these are fantastic tools to visualize atomic structures. Especially Vesta is used for density functional theory mainly, while Ovito is used for molecular dynamics and have something like coordinates and number analysis and so on. So these MD simulation can be used to predict or calculate properties. So these properties could be mechanical properties, transport properties, stress strain curve, and so on, that we discuss also in the DFT module, thermodynamic interface property, and so on. So here in this particular example, we have polyethylene, and we're trying to simulate the stress strain curve of amorphous polyethylene. So yeah, that can be useful for mechanical engineering applications. And not just that, we can have several structural properties such as radial distribution function. So it's basically the probability of finding a pair of particles at a certain distance. So when you are trying to move the atoms with particular forces that is governed by a particular force field, we might want to see how those atoms are changing their position. So that is can be captured from RDF. Those displacement of each atom can also guide you to calculate something called diffusion or mobility of the atoms. So using mean square displacement, you can also calculate the bond length and angle changes, coordination number changes, basically how many nearest neighbors. So we have in a particular chemical or local environment, density profile. So as I said, it can be used for radial distribution function, which is basically you have the atom in the middle, and then you take a radius of r and radius plus delta r, and you can calculate how many atoms are there, and that will give you kind of the average distribution of atoms around each atom. It will not give you angular distribution and dihedral distribution. So there are different type of distribution as well that can be calculated, such as angle distribution, dihedral distribution, and so on. Another important quantity that can be calculated is autocorrelation function. So the autocorrelation function can be defined and calculated for any particle or quantity such as velocity or any system. And so it basically is used for the diffusion coefficient of the particle. So you know the velocity at 0 and velocity at t, and we can integrate this to calculate the diffusion coefficient. We talked about the mechanical properties in the previous module as well. That can be done here in molecular dynamics as well, such as elastic constant, stress strain curve, yield strength, transport properties, ionic conductivity, electrical conductivity, thermodynamic properties. This is a huge list. I'll just put it there, but we'll be primarily focused on the mechanical properties, interfacial properties, chemical properties, spectroscopic properties, infrared Raman spectra, and so on. But as I said, we'll be focusing on mechanical properties only.